Topic 8, superposition. Part 4, diffraction, which means scattering or spreading out of waves. This diagram here shows these straight waves, which are called plane waves, are moving towards this big gap here. And after going through the gap, they spread out of it, as you can see. If you join up these edges here with a line, and join up these edges here with another line, and extend these two lines backwards like this, then the angle formed by them is small, which means the amount of spreading or scattering or diffracting is small. Now the same set of plane waves as the previous slide is moving through a smaller gap, as you can see. And you'll notice that the amount of spreading or scattering or diffracting is much bigger. So if you draw a line here like this, do a line there like that, and join them up, and the angle formed is much bigger. When the size of the gap is about the same or smaller than the wavelength of the plane waves, then the amount of scattering or amount of diffraction is maximum. In other words, these waves spread right around like this. Some notes on diffraction. Don't forget to copy down the definition. The first point is diffraction is the spreading of waves after going through a narrow gap or a slit. Second point is the spreading of waves can also occur at an edge. And the extent of diffraction or the spreading depends on the size of the obstacle or the width of the gap compared with the wavelength of the waves. You can print out this page and practice drawing in diffracted waves on both diagrams. This diagram on the left has a small gap, therefore the amount of diffraction will be very significant. It will be something like this. The waves spread right around like that. This one here has a big gap, therefore the amount of diffraction will be small, so the diffracted waves will be something like this. The main thing to remember is that the diffracted waves has the same wavelength as the plane waves. Waves also diffract around edges and obstacles. Look at this one here. Here is the edge or the obstacle. The width of it, it's about the same as the wavelength of the waves. So the amount of diffraction will be very significant. The waves will spread right around here. So it'll be something like this. All the time keeping the wavelength of the waves constant. Look at this one here. The width of the edge or the obstacle is much smaller than the wavelength, so the amount of diffraction will be very small. Like this, just a little bit. Keeping in mind that the wavelength of the diffracted waves should be the same as the wavelength of the plane waves. Here you can see the width of this edge or obstacle is about the same as the wavelength of the waves, so the amount of diffraction is very significant. Think about this question in terms of diffraction as sound waves travel through a door. What happens when we have two narrow gaps side by side like this? This gap here will produce its own set of diffracted waves like this. And this one also will produce its own set of diffracted waves like that. And so on. So the end result is you will get two sets of waves being superimposed on top of each other, producing what we call two slit or double slit interference pattern. This photo shows that water waves do in fact diffract like this. But remember, the wavelength here is the same as the wavelength there.